Thank you. Thanks, Alex. Well, good afternoon, everyone. I am JESÚS BARRASA. I work for Neotechnology. I'm a field engineer. I'm based in the London office. And you will be surprised to know that I will be talking about graphs. And in particular, two types of graphs, the RDF graph and the property graph that implements Neo4j. So I have to say that I'm quite happy with the turnout. I mean, taking into account that next door is Mark Abra talking about Panama Papers and Cisco upstairs. So, well, I think it's a bunch of brave people coming here to listen to things about RDF. Well, anyway, let me start with a quick show of hands. How many of you use RDF in any way, or linked data, or that explains it? Good. Right. So for those of you who do, I mean, what for? I mean, is it about interoperability? Is it about you publishing data as RDF? Anyone? Is it about you consuming public data available as RDF? Is it for search engine optimization? Take it as a separate case compared to the first one, because you probably know that these days, you know, with the whole Google knowledge graph, if you publish your data as structured data, as RDF data, using a JSON LD, well, the Google crawler will pick up this information and add you to the knowledge graph, and then when people search for your information, you will get, instead of the boring organic search results, you will get these kind of nice snippets that Google produces. So that's another interesting use case. Is it for data integration, any of you guys? Those who use RDF, is it for data integration, bringing data into a graph, and then working your way to link it together? Or do you do reasoning? Do you do semantics? Good. Great. Sounds good. OK, let me quick refresher for those of you who are less familiar with it. Just a bit of history on where these two models come from. And, well, RDF stands for the Resource Description Framework, and it's a standard, W3C standard, for data exchange in the web. It's an exchange model. And it represents the data as a graph. So that's the main point in common with Neo4j, with the property graph. So it understands the world in terms of connected entities, right? And it became very popular at the beginning of the century when Tim Berners-Lee and Jim Handler or Lassila published this article in Scientific American called The Semantic Web, where they described their vision of this world, this internet, where people would publish the data in a structured format with well-defined semantics in a way that agents, as they call it at the time, software, would be able to consume it and do clever things with it. So that was, again, a few years ago, nearly 15, 16 years ago. And then, of course, RDF, persisting it, storing it, became a thing. And stores were called triple stores, then they called quad stores when they added information about context and named graphs. They also called themselves RDF stores, and more recently they called themselves something like semantic graph databases. Well, I'm going to try and analyze what do they mean by that, how do they relate to what Neo4j does, and what does this semantic mean. On the other hand, the label property graph, at more or less the same time, this group of Swedish engineers were developing a CRM system, and they decided to model data as a graph, store it, and they had different motivations. It was not so much about exchanging, publishing, and being interoperable with other, if that's a word. I mean, they were more interested in efficient storage in order to be able to do fast querying, fast traversals. And they like this model, this way of representing data in a way that's close to the way we understand the world. I mean, something that's close to our logical model, to the way we draw a domain in a whiteboard. So, and they thought, of course, that had value outside the CRM that we're developing, and actually that, a few years later, became Neo4j. And the model that it implements is called the label property graph. So taking into account the origin of both things, one, it was more about data exchange, and the other one is purely storage and query. Let's now look at the models, I mean, the models that they implement. So you all know by now that a graph is formed of two components. It's vertices and edges that connect them. So how do these two appear in both models? Well, label property graph, vertices are called nodes, and nodes have an ID, uniquely identifiable, and they have a set of properties, a set of key value pairs that characterize them. In the same way, edges connections between nodes. We call them relationships. They have an ID. It's important. We can identify them uniquely. And they also have a type and a set of key value pairs, key properties that characterize this connection. So important thing to remember here, and if there's a pointer here, hopefully, yeah, is that they both have internal structure, and that's important. That differentiates it from the RDF model, as we're going to see in a minute. So both nodes and relationships have internal structure. And by internal structure, I mean this set of key value pairs that describe them. Right? You have a little diagram of that. On the other hand, the RDF model, it calls the vertices. Well, vertices can be two things. At the core of RDF is this notion of triple. A triple is a statement, and it's composed of three elements, which actually represent two vertices connected by an edge. It's called subject, predicate, object. And, well, subject will be a resource, will be a node in the graph. The predicate will represent an edge, a relationship. And the object will be another node or a literal value. But, yeah, from the point of view of the graph, that's going to be another vertex, right? So interesting thing to know is that resources, which are the nodes here, are identified by a URI. A URI is a unique identifier. Well, you know what the URI is, right? And same with relationships. Edges, as we've seen, are identified by a URI, which means that nodes or edges don't have internal structure. They're purely a label, a unique label, a unique identifier. So that's one of the main differences. Going to look at an example, which is going to make it a bit more clear. So I've picked one of these rich snippets that Google returns when you do a search. I search for sketches of Spain, which is one of my favorite albums by Miles Davis. And what you get is this information, so description of the album and things like the artist, the release date, the genre, producers, etc., and some words. So this information, I'm going to try to represent it in both models, and we're going to see what they look like. So that's RDF. That's one of these possible serializations of RDF. That's what's called n-triples, but we're probably going to look at the turtle syntax. Exactly the same information, but in an alternative representation. You still can see hopefully, the triples. So triples are identified by a URI, as I was saying. That will be the subject. The predicate is the name, and the object will be sketches of Spain. So it's a sequence of triples. I mean, I'm not saying that this is a big differentiator. I mean, the syntax between the two models, but that's the kind of thing that you will have to write if you want to insert data in a triple store, right? Right, so that's one of the models. And the other one, well, important. Let's look at it graphically, because that's quite interesting. So as we mentioned before, this bit of information would look something like that. And we noticed that, well, this node here, probably not very readable. Sorry, that's produced by the RDF validator. That's in the W3C page. But this node to the left represents the album, and it has a set of edges coming out of it. Some of them are rectangle. These represent literal values. In particular, this is the description, album by Miles Davis. This is the genre. This is the title. And it has connections to other things that are like an ellipse, an elliptical shape there, that represents other resources, other nodes in the graph that have their own properties, right, their own attributes. What this means is that by representing data in RDF with triples, we're kind of breaking it down to the maximum. We're doing a complete atomic decomposition of our data, right? And we end up finding nodes in the graph that are resources, but also literal values. Now let's look at it from the point of view of the label property graph. And what I've written here is a sequence of cipher statements that contain exactly the same information. So semantics are the same. We create, there's not a standard serialization format, a way of expressing a label property graph, but I think a sequence of create statements could do the job here. So we see that we create a node. The node is more obviously represented with a parenthesis there, and then the attributes, the internal structure, as I called it, is in these curly brackets here, the name, the description, the genre, same with the detailed description about it, and then the connections between nodes are described like this. Don't want to get too much into the details of the syntax of how you create that, but that's what the graph looks like. Well, the first impression is that, well, it's much more compact. It's completely different. Well, completely different. Has bits in common. But because nodes have this internal structure and attributes, values of attributes don't represent vertices in the graph, we have a much more reduced structure, as you can see, right? So we still have the album at the center. That's connected to a number of entities. But the title, the name, the description, they're not represented by separate nodes, right? So that's a first distinction. And that's it's interesting because when you compare them, of course the information will be stored. But when we compare, sometimes there's this confusion. I mean, I have a graph with a 2 billion triples. How does that compare in terms of nodes, for example? Well, if I take a modest description of what a graph may look like, so take a graph with n nodes, and what, for example, 5 properties per node, 5 attributes, 5 relationships, 5 connections, can be many more, but just to give you an idea. In a simple model like this one, well, we would get 11 triples per node in a labeled property graph. I mean, again, I'm not comparing storage capacity, blah, blah, blah. I'm saying that keep in mind that when you say this is a 100 million triple graph, RDF graph, that's roughly, in a graph like this one, is sort of an order of magnitude bigger in terms of nodes than the labeled property graph. So that will be probably equivalent to a 10 million node labeled property graph. Good. So we now know a little bit of how the two models compare. The next thing we're going to look at is not the syntax, but what are the differences in terms of expressivity. And the first one, and it's quite important, is the fact that in RDF, it's not possible to uniquely identify instances of a relationship. It can be said in other words like this. It's not possible to have 2 connections of the same type between the same pair of nodes, because that would represent exactly the same triple. So it will be no extra information, right? In an example, a bit silly, we like this Dan likes Anne example in our slide decks. So Dan cannot like Anne 3 times, can only do just once. Let's look at an example of that. Labeled property graph. We have this statement here. We create a node called Dan that likes Anne. And I repeat that Dan likes Anne and Dan likes Anne once more. What I get is this graph with 3 connections of type likes between Dan and Anne. Good. I can not only visualize it nicely, but I can query it, and I can say, how many times does this pattern appear in the graph? And I get a count of 3. Now let's try to do the same in RDF. So that's Sparkle. What we would do is an insert statement where I say, well, Dan has named Dan, as we did before. Anne has named Anne. And then Dan likes Anne, Dan likes Anne, Dan likes Anne. What I get instead, look at the graph here. Remember this explosion, because in the sense that we have the values of the properties as vertices of the graph. We have Dan that has named Dan. We have Anne that has named Anne. And we have a single connection between them. Sad, because he liked her 3 times. Right, so if I do the count again, and I search for this particular triple pattern, Dan liking Anne, and I do the count, I get 1. And the reason for that is I was saying, it's not possible to identify unique. Oh, it is. We're going to see in a minute that there are alternatives, quite horrible ones, but we're going to see it. So that's one of the main differences. So you can't identify individual instances of properties of the same type, relationships of the same type. Second one, because you can't identify them, you cannot qualify them. You can't give attributes to it, right? So you can't have attributes in relationships in RDF. Another example. The connection between New York City and San Francisco is, well, $300 and 4,100 kilometers. Again, this statement can be expressed in cipher, which is near for JESÚS query language, saying that there's a connection between New York City and San Francisco, and the connection has 2 attributes, the distance and the cost in dollars, right? I do that, it produces this nice graph, and I can query and say, this connection, what's the cost, what's the distance? And I get the 2 values. Good. I try to do the same in RDF, and again, have this trouble, because I can say that there's a city called New York, a city called San Francisco, and there's a connection between them. But how do I state the fact that that this connection has a cost? Well, I could try to say something like connection has a distance, but which connection? That would be a kind of a global property of the connection, so you can't express that in RDF. And here's the graph that produces, right? So there are alternatives, as I was saying. One of them is, of course, modeling workaround. So you model things in a different way. And we're going to see that that's the problem that we've been having for a few years with the relational model. What happened when we had these many-to-many relationships? So people knowing some people and people being known by others. I mean, that's fine in your entity relationship model, but when you have to translate that into tables, you have to create a join table. So because the modeling paradigm doesn't offer you a way of modeling that, you have to use what you have at hand and represent it the way you can. The problem with that, as you know, is that that starts building a gap between your model, as you conceive it, and the model that you store and that you have to query, right? And we know where that gets us. So we will see that there's a possibility, of course, of having a modeling workaround. And there are 2 more technical approaches called reification. You have the links there, and singleton property that are, I have to say, not nice. What you're going to see is not nice. So those of you who are under 18, cover your eyes. Modeling workaround, simple one. So that's OK. So we don't have attributes in relationships. So what I'm going to do is I'm going to create an intermediate node, right? So that's what I can do in the label property graph. In RDF, I can't. So what I'm going to do is I'm going to create an entity that represents the connection between New York and San Francisco. And then once I have a node, I can get properties out of it, right? I can get the distance. Fine. OK, that's not too bad. I mean, the querying will get a bit uglier, but OK. Now, verification. It's not very readable. We still have here at the top, if you remember, that's Dan with his name, Dan. And that's Anne with her name, Anne. And there's a connection saying that he likes her. What we're doing with verification is we're creating a metagraph on top of our graph that represents the statement that we have here. So we're creating a new node that represents a statement, right? And it's typed a statement here. And it points at the subject, Dan, at the object, Anne, and at the property that I'm stating, the fact that he likes her. And now that I have an object, now that I have a node, I can say, well, let's add a counter. 3 there. Ugh, quite ugly, right? Well, that's one approach. You can imagine what happens to that, right? On the good side, you still can query who does Anne like, right? Because you still have the, remember on the top right? We still have the model itself here. But now if you want to query how many times, then you have to go and look at the graph and the metagraph. So if Dan likes Anne, then now look at the statement that connects Dan and Anne and get the counter. Ugh. Imagine if you need to update that. I mean, you have to say, Dan has liked her once more, right? You wouldn't come and say, add one more fact, because that doesn't add more information. You will have to come and say, OK, go grab the pattern, take the value in the counter, increase it by 1, and then set the new value. So you're kind of working with a meta model, which makes things quite horrible. I mean, I don't want to spend too much time on that. The singleton property is another alternative, pretty much in the same vein. So you have your original model. You have Dan with his name, liking Anne with her name. And what you do, well, not liking, actually. What you're doing here is you said, can I not name relationships in a unique way? Well, yeah, let's do it. I'm going to call it ID 1, 2, 3, 4. OK. Now that I have given it a unique name, I can say things about it. And I can say 1, 2, 3, 4 is actually an instance of likes. And I can now give it a counter of 3. Again, I'm building kind of a meta model. And that probably might be more compact than the previous one. But now you cannot ask directly here, who does Dan love? Because he's not, like. He doesn't like her. He's 1, 2, 3, 4 her, right? So you will have to say, what does that mean? Well, that is type likes. So you can imagine what, again, the querying looks like and the updating and all that, right? It looks like, well, exactly, but that's the problem. So, good. Third difference. So, and that's on, well, RDF can have multivalued properties. So you can have triples, where the subject and the predicate are the same, but the object is different. That's absolutely fine. In the label property graph, what you have to do is use arrays. So if you want to have a sequence of values, so that's the equivalent. And, well, I have an example here. In the snippet that we had before, we had the album that had 2 values for the genre property. So we have jazz and orchestral jazz. Easy, 2 triples. That's easy to express. In Cypher, you need to use an array. Not too bad. And finally, another difference is this notion of quad. I mean, you can add to triples what is called a context or an extra value that identifies, makes it easy to define subgraphs, to define named graphs, as they call it, right? And that's something you just can't do in the label property graph for now, right? So we can do things like, stating that Dan likes Anne in graph 1, but then having that Anne likes Emma in another graph, right? And then when you can query it, you can specify which graphs you want to query. So that's quite a handy thing. Good. So we've looked at some of the differences in the models and the expressivity of them. We've also looked at the query language, so I'm not going to spend too much time on this. So you've seen that because of the this atomic decomposition of the data in RDF, well, you typically will have longer patterns when you ask queries like, for example, this one, names of the artists who have albums produced by Irving Townsend. Well, you're exploring this portion of the graph, and therefore you have 4 patterns, each one representing each of the edges. In the label property graph, because it's a more compact one, typically the query will look But again, that's not, I would say an essential differentiator, okay? Right, regarding the updates, probably worth mentioning that, well, they were recently added to Sparkle, and I mean, I find that a bit cumbersome, that's all, but anyway. So you can, in something like uppercasing the values of a property is very much SQL-like in Cypher, so it's very simple. You match a person and attribute name to uppercase. Whereas in Sparkle, you will have to match it, then bind it to a variable, do the uppercase, and then do the insertion and the deletion, because remember that we can have multiple values. So by updating, you need to delete the previous value unless you want to keep both of them, right? Okay, again, these are syntax differences. What about the stores? Well, very briefly, I don't want to go into vendor comparison or benchmarking or anything, but RDF stores are very, very strongly index-based, right? So, and Neo4j, on the other hand, is navigational. So it implements index-free adjacency, which means that it stores in disk the connections between connected entities, between connected nodes, right? Which means that when you query it, you're actually chasing pointers instead of scanning indexes, right? That's the main difference. And we know that index-based storage is okay for not very deep queries, is okay, but don't try to do things like path analysis, as opposed with Neo, where you can have this native storage that's excellent. It's the top approach for variable length traversals, from shortest path analysis, et cetera, et cetera. Right. And it's also fair to say that, well, triple stores were never meant to be used in operational and transactional use cases. So mostly, I mean, the way you find them used is in scenarios where data sets are mostly additive or slow changing, if not immutable. If you think of these big, large knowledge bases, I mean, the capital of Spain is going to be Madrid, and that's not likely to change. So that's the kind of information. I'm not saying that it can't take updates. Of course it does. I'm just describing the most common use cases. Whereas Neo, again, excels in highly dynamic scenarios with high volumes of reads and writes and transactionality and data integrity is key. So yeah, we've done a bit of comparison, and we got to the point where we have to talk about semantics, which is the other possible differentiator. So what do we mean when we say semantics? I'm going to give another show of hands, but they have three. Oh, it's meant to be gray, white, fine. But anyway, the first two lines, I can see the first two lines are RDF, and a fragment of RDF in turtle notation, right? So saying John Smith lives in London and London is a city in England. The second one is a fragment of JSON that could easily represent the same information. The third one is JSON LD, right? Including both the data and the ontology. And the final one is a fragment of Cypher. So my question is, what do we mean by semantics? I mean, are any of these fragments of data more semantic than others? And if so, what does it make it semantic? Well, I'm going to try to answer the question. I think that semantics can mean two things, right? And at least in RDF, in the RDF world, these are the sort of two valid ones. The first one is the idea of vocabulary-based semantics, right? So because you can identify relationships with URIs, you can define agreed vocabularies, like schema.org. That's one good example, right? Which is the one that's used by the Google Knowledge Graph, right? And it's basically most of the usage. This is the kind of semantics that people refer to. I mean, because I'm using this vocabulary, people can understand me, right? But then there's the other one, which is the inference-based semantics, right? Where what I want to do is express what my data means so that I can do things like inferring new facts, so do some reasoning, or checking the consistency of a data set, try to find whether there's a contradiction in my data set. Okay, let's look at an example, because these inference, I'm going to focus obviously on the second one and how that's exclusively of RDF, if it is. So it's no magic, although you might hear that from some vendors or some people that want to make you think that it is. So let's look at example one. I mean, example one, I'm looking at a simple pair of facts. John lives in London, and London is in England. So you can express that with two triples, right? John Smith lives in London, and London is a location in England. Now you run a query, who lives in England? You can express that in Sparkle here. And one would say, well, RDF Semantics is going to figure out that John lives in England. And of course not. Of course, you get no result. Because there's no magic there. Someone has to tell. I mean, we have to make explicit. There's a missing link there, a missing connection. Someone has to say that if someone lives in a city and the city is in a country, then you live in the country. But no one's going to figure that out if you don't make it explicit in a rule, for example. That's an example of how you can make the semantics explicit. So it's not about being semantic or not being semantic. I mean, are your semantics explicit? That's the key question. And, well, that's one way of doing it. Another example well, we can ask the question again, and now we would get John Smith, right, if you infer the new facts. Another question, more in the integration space. So you're bringing data from two data sources into a triple store, and you say, well, there's two facts coming from data source one. Jane Smith has this email, and her Twitter handle is this one. That can look like these two triples, okay? Now we get another pair of triples from another data source where we say that Jane Smith, her email is again the same one, and her LinkedIn profile is this one here. Again, that looks like these two triples here. And you would say, oh, that's integration, magic. We put it in the RDF graph, and semantics are going to do the magic. Let's ask the question, what's the LinkedIn profile of the person that's tweeting as J. Smith? That's the Sparkle query that would ask the question. And you would say, that's going to be clever and say, well, the email is the same, so I'm going to match the duplicate. Well, and of course, you get no results. Because again, like in the previous case, you have to say that email address is a unique identifier, and therefore you can infer that if two resources, right, have the same email, well, you can derive that they're the same, and that can be expressed with a rule like this one, for example. That's not the only way, because there are the hardcore semantic web people, the owlers, as they call it, the people that like the OWL language, that would express it in a more elegant way, if you want, which is like saying email address, has email, is an inverse functional property, right? For those of you who are, any people familiar with OWL? Good. So that's a way of saying, basically, that an inverse functional is a primary key style property. I mean, it's not exactly the same, because a primary key is kind of a constraint which would prevent you from adding data to your database if there's another one with the same value. Here, you can add data without any problem. The thing is, if we find two that have the same value, we're going to think, well, these two are the same. So it's more inference-based. And then, but anyway, I mean, even if I express it like this, which is kind of a more declarative way, these great part here are the semantics of inverse functional property, right? I don't want to get into the details, but basically, if two values have the same, is exactly what I just said, have the same value, then I can derive that they are the same. So if I do that, then fine. I rerun the query, and I will get that the LinkedIn profile of that person is this one here. I like to bring Tim Berners-Lee here, because the thing is, it's all about making the data explicit. I mean, there's no magic, there's no AI. I mean, RDF is just a way of making data more intelligent, right? It's making data, making your semantics explicit, right? So taking the effort of doing that. So what do we need to have a semantic graph database? Well, first we need a graph database, of course. And the second thing we need is we need to represent, to make explicit the semantics of our data, right? And then we're going to need an engine, right, that's going to be able to do some kind of reasoning, whether that's deriving new facts, whether that's detecting inconsistencies. It will depend. So we do have that, and I'm going to try to show how we can do that with Neo. Good. Is it readable? But not very much. Anyway, it doesn't really matter. So, what I'm going to show is some features, some capabilities that are typically from RDF as stored procedures, and stored procedures and managed extensions. Hopefully, they will make their way into the APOC library soon. So the first thing, what model am I working with? I'm working with the movie database, the one that comes with Neo4j. So it's a pretty simple data set where we have movies at the center. It's the green note here. That's connected to actors, directors, producers, screenwriters, and critics. It's a slight variation of it, but pretty much is the same. So we can query it. I'm going to make that a bit bigger, maybe. Any better? Hopefully. And actually, I've learned that trick from Alistair before. Should be even better. Good. Right, so we have a query here that finds a movie called Unforgiven, and I'm getting all the entities that are connected to it, just for you to have a look at it. So we have the movie at the center, and we have actors that acted in the movie. We have directors. In this case, Clint Eastwood is a director and actor as well. And we have critics that review the movie. So that's what the model looks like, pretty simple. So first thing I'm going to want to do is, well, we've seen that the labeled property graph and RDF are graph models. So it should be pretty straightforward to being RDF an exchange format. Why can't I not serialize my data or expose my data as RDF? Well, you can. And as I sort of right, it's trivial. And what I built is an managed extension where we can run a request, identify nodes by ID. And what I do is I run a query, a request, and it produces RDF, right? It's producing the RDF description. In this case, it's using JSON LD notation. It's one of the possible serializations of RDF, containing the information about the resource that I've selected, the node that I've selected, well, its type and the relationships, the other resources it's connected to, and the literal properties, right? So pretty simple. That's a direct translation, of course. And of course, we can run that from a command line, which would be very similar. Let's clear that. Because the thing is, RDF, we said it's a data exchange format, so it has multiple serialization possibilities. So another alternative is RDF XML. So it's exactly the same extension. I'm running it with the same ID, but I'm producing RDF XML. Same bit of information, different serialization. Let's look at another one. We can use as well, I think text turtle is the other one. There you go. So still another difference. It's same information. As you can see that we have the same node, the type, but we're exposing data as RDF. So that will be use case one. Now the other case that I want to show you is the one about inference. So we have our model as we've seen, and what I've done is I've defined an ontology. I've made my semantics explicit in a very simple hierarchy. That's what it looks like. So I've defined three types of entities, three categories, director and actor, and I've specified, I've described them as being director, a subcategory of artist, and actor, a subcategory of artist as well, right? Good. So we've seen that there are directors in our database. Okay, we've seen that there are actors in our database, but I don't see any artist, right? There's not a single node labeled as artist, okay? So what I'm going to do is, okay, I want to query all the, let's again pick a similar query to the previous one. I want to get all the individuals connected to this movie, Cloud Atlas, and now I say, yeah, I would like to refine these, but just get the artists. And of course, I could express that in Cypher and saying, well, artists, we've defined them as directors and actors, so I could extend my query to get exactly that. But then what if the definition of artist changes, right? And I decide to include the screenwriters, I would have to change my query. So I would like instead, and it would be quite cool, to be able to try to get artists, right? The problem is if I try to do that, well, for starters, Neo is telling me that that label doesn't exist, that has not been defined. There's not a single node in your graph that has this label. But I've defined semantics. So what I've done is I've created a semantically enabled endpoint, which basically is again an unmanaged extension, as you can see. So I'm calling it with sending a post request, as I did before. And I'm sending exactly the same query. I'm sending a Cypher query that's looking for artists that are connected to the movie Cloud Atlas. The difference here is that it's not the standard Cypher endpoint of Neo4j that we use in the browser. And this one, instead, what it's going to do is going to analyze the query. It's going to find the labels. It's going to say artist. Do I know anything about artists? It's going to query my ontology, and it's going to say, well, artists can be directors or actors. And it's going to expand the query and hopefully return some results. There we go. I run this, and I get a list of artists, the subset of the people connected to the movie that are in this category, right? So that's what's happened. It's quite nice, and it's telling me that the expansion has been of 2 classes, and, well, the time it's taken. We were saying before that maybe this definition of artists can change over time, and we can precisely do that. We can say, okay, now from now on, directors are not considered artists. So I'm going to remove them from my hierarchy, and I would say, well, this is, again, a cipher query. The interesting thing here, as you can see, is that my ontology is part of my data. I'm not recompiling. I'm not doing anything. I mean, the code is the same. I'm just saying that now the category director, which used to be a subcategory of artist, I'm going to delete that. I'm going to remove that link. So it's not going to be a category anymore. Good? So if I look for my categories again, we see that the director is isolated here, and the only type of artist are the actors. Right. So the good thing is that my old query that I just ran through my, of course, semantically enhanced endpoint would still work. But it's going to return a different data set, a different set of results. So it's going to return only the actors. So if you see, now the expansion only was expanded, of course, to the actors, and I'm returning, right, those artists, I mean, those entities connected to the movie that are artists, right? Good. So yeah, and of course that can go on. I mean, I can extend it to define a new category. That's, for example, film industry people. So I can say, well, and that includes both the artists and the producers. So I can extend my ontology, and that would look something like this. Now we have film industry people that contains producers and artists, which used to contain actors. So I can rerun my query. Well, I can run another query actually on film industry people, which is again a category that doesn't really exist in my graph. So effectively, what we're doing is we're inferring new information. We're running inferences on the fly, right? So that's what we're doing here. So, and that will bring all the connected entities that are effectively artists according to the, film industry people according to the new definition in our ontology. Good. Right, so that's the, let me go back to the slides to conclude. So what are the takeaways from this session? Don't know if it's made sense so far. Good. Okay. It takes a couple of minutes. Few takeaways. Right. So the first one, and that was mentioned just a few minutes ago in session by the Financial Times by one of the developers who came to present, and they said, well, and they actually done the transition from RDF to the label property graph, and they said, well, we thought what we needed was a connected data, a linked data platform, a semantic platform, but what we actually need is a graph. So ask yourself what you need. I mean, what kind of features do you need? Is it about the inferencing? Is it about the semantics? Or is it because it's a graph? Because there's a lot of value in the graph, right? And the second question is, so are you telling me that if I'm not using semantics, if I'm not running inference, I'm not being semantic? Well, I don't think. I mean, you have a graph. I mean, that's the thing. In most of the use cases, and I've spent a few years in previous lives working in RDF, you find yourself not using as much of OWL and all the semantic capabilities as you would, because it's extremely complex in the first place, and I agree with Dan from the Financial Times. And then you have the problem of performance. If you're working with a reasonable size data set, don't expect it to finish well, even to finish, right? So, and well, we see that publishing RDF out of Neo is trivial. I mean, I didn't share the code, but it will be available in GitHub. You see the link there, and it's under 100 lines, so it's nothing. It's a graph, and exposing a graph in RDF, it's trivial. It's nothing. And same with importing. I didn't show that because it's a more boring example, but ingesting RDF into Neo is again a simple task. And then I've proved that inference does not require OWL and RDF. Of course, it's a simple example, but what I mean is that semantics, in the end, is nothing else than this sort of data-driven server-side logic. So you're putting some intelligence on your data, close to your data, and that's driven by some data, by an ontology, right? And well, if you manage to, as you see, to balance the express, if you find the right language for your problem, you can find it a useful tool. But I mean, I'm not going to criticize OWL because their own creators, you can Google that and they can see why they discuss why it's not being adopted. You can Google this talk by Jim Handler. So it's definitely not taking off, and I think one of the reasons is because it's kind of overkill problem for most of the use cases. But anyway, that's the end of my talk, and thank you very much.
Thank you.
Questions?